Okay, so today I'll tell you about double and triple integrals. Let's begin first just by recalling the integrals you already know from Calc 1, right? So what are the integrals that you are familiar with? Well, essentially there were of two kinds. First, you had like the indefinite integral, or sometimes called the antiderivative, right? Which was an expression of this form, where you had like a function and you would integrate it without specifying any bounds here, and this was supposed to give you a function whose derivative was the function that you have inside, right? On the other hand, we had this definite integral, which again you're given a function, but now you specify some bounds, and if you wanted, when you think of the graph of this function, you would interpret this expression as some sort of net area. Or area under the curve. So of the two kinds of integrals, the antiderivative and the definite integral, really the one that we'll be mostly interested for today is the definite integral. The antiderivative, well, we will use something that's similar to that idea a bit later once we talk about how to find potential functions. But for now we will mostly ignore it. But the idea will be that we will focus on this definite integral, which in practice, again, this is sort of the good thing of this course. The philosophy is really you're not learning any new tools. Really, you're just using the tools from Calc 1 to study more complicated problems. So we're going to generalize this concept of definite integral, but you'll see that in practice, the way in which we will compute them is by computing individual definite integrals of one variable. In the same way in which when we talk about partial derivatives, really you were just working with one variable at a time, so you could just apply the same rules of differentiation from before. And now we'll do something similar. We will just apply the same rules of integration that you already know. And so in this video, I'll just explain more or less what the idea is, and then in the next videos, I'll do some examples. So let's just talk a little bit more about this definite integral. To keep in mind how it was really defined. So when you had this function y equals f of x, and say here's A, here's B, then this chunk of area was supposed to be the definite integral, right? So this area was supposed to be the integral of f from A to B. And in general, right, as you may remember, this is more accurately a form of net area. Because the point was, for example, that if the function that crosses the x-axis and becomes negative, then this piece of area would be counted negatively, and this piece of area would be counted positively. And that's okay, because if you actually wanted to use the actual area, compute the actual area, meaning compute taking everything as a positive quantity, then you would just use the absolute value of the function. but this gives you some sort of gives you more freedom when trying to interpret the definite integral. And so the important thing here is really how it was defined. This is something that maybe you saw in your class, but really did not use that much, which is in terms of partial sums or Riemann sums. And so the idea is that if you really wanted to compute this area, what you would do is something like the following. You would take this interval and subdivide it into pieces. Right, maybe here you would put, let's say, x1, x2, x3. Okay, so here I'm dividing this interval so that I have 1, 2, 3, 4 subintervals. And now imagine drawing for each subinterval a rectangle whose height is the value of the function at some given point in this interval. Doesn't really matter too much which point on the interval you're choosing. The main takeaway from this approach is that you're trying to say that the area we're actually interested in, which was this one, can be approximated by the area of these rectangles, and that as you start shrinking the size of these rectangles and adding more and more subdivisions, then this approximation keeps getting better and better, right? So imagine now that I actually introduce more subdivisions. Then the point is that here the area of the new rectangles combined will be like a better approximation to the area you're actually interested in. Okay? And in practice, again, maybe you did not use this too much to compute actual integrals, but that's sort of the main idea behind the definition of the definite integral. And now we want to do apply a similar approach to the case of a function of two variables. And the case of three variables would be exactly the same, although that one has a disadvantage that you cannot really draw it very well. And so let's talk about double integrals. So for a double integral, before we were writing y equals f of x, now we have to add an extra variable, and so we would write z equals f of xy. Okay? And again, the graph of a function of a single variable looks like a curve. The graph of a function of two variables looks like a surface. So here's an attempt of a graph for the surface. And before we would talk about the area between this curve and the x-axis. Now it makes sense to talk about the volume between this surface and the xy plane, which is the floor. So before you had to fix some interval, right? Here you were working with some interval. So imagine that you choose an interval here, AB, and you use an interval here, CD. Okay? So really that gives you like some rectangle downstairs, and from this rectangle you sort of lift that up and get a tower, and this tower will pierce the surface and give you something two-dimensional upstairs, and the volume, right, the volume between this surface and the floor is really what you would like to call the double integral. So let's try to write that more precisely. So okay, so before let me just introduce some notation which I haven't used here, or remind you about it. Right, so you think here of f as the height, dx as a width, right? So this is like the height times width has units of area, right? And you imagine that the height is like f of x here, and the width is like the x, right? Now the height is, you do like a similar approach on this side. So you have some length dx here, some length dy here, so you get a tiny area which we'll call dA, right? Which you can think as dy dx, which is really the same as dx dy, although we have to be a bit more careful. Part of the main point today is what happens when you write this in different ways. But so let's just think about this in terms of the area. And so you have a tiny piece of area here, and that gives you a tiny box, right, of height f of xy. So our notation for this double integral is going to be something like this, okay? And before we would specify the bounds of integration as being a to b, because that was the smallest and largest value of x. For now, if you call all of this region R, all this blue region R, then we are just going to write here R. In a moment you'll see that the point of writing two integrals is that one will be like from A to B and the other from C to D. It's just that you have to be careful about how to write them appropriately. But so this means, again, you should think about it as volume, although sometimes the surface may go below the floor, right? And when that happens, which is when the function becomes negative, when that happens you want to consider this volume as negative. So again, in some sort of this double integral, you should think of as a form of net volume. Between the part of the graph so there's the volume between the part of the graph, right, of the function which is above R. And the xy plane. Okay? So, basically, you have to ask then, really, how would you define it? Right? And the idea is to follow the approach from before. So before you were approximating the area with these rectangles, and now what you would like to do is approximate the volume with these boxes. So really you define this approximating the volume, the real volume with the volume of the boxes. The volume and the point is that as you make more thinner boxes, then this approximation will start getting better and better. So for example, here I drew a box, but here you could also draw another one. Okay? And you imagine that you draw more and more boxes downstairs. So you put here one and another, another. So you start partitioning the domain, the region of integration, into subrectangles. Okay? So you use smaller subrectangles to improve the estimate. So I'll show you in a couple of seconds or minutes how this is supposed to look like on the computer, so that it becomes more clear. Okay, so let me show you with this illustration the geometric interpretation of the double integral in terms of Riemann sums. So again, the idea is that you have some function, which in this case is x squared plus y squared minus 1 times 0.2, and you think of the graph of that function as a surface, which is this pink graph that you see on the animation. Okay, and then the double integral under this interpretation is the volume between this surface and the floor, in the same way in which the ordinary single integral is the area between the curve and the x-axis. And so in this case you can approximate the volume by using these green boxes that you see here. Let me just show this to you from a different perspective. And the point is that depending on how many boxes you use, the approximation keeps getting better and better. So for example, as I make the boxes thinner, right, which is what's happening here, you see the total difference between the volume between the surface and the floor versus the volume of all those green boxes added together keeps getting smaller and smaller. So the idea, as in the case of the ordinary single integral, is that in the limit, which is what's going on here, where you take really thin boxes, in the limit the difference is supposed to go away. Okay, and that's how you would define the double integral in terms of the approximation of these partial volumes. Now, so the question is, how would you find this number, right? So for example, before, when you were trying to find something like the integral of 1 from 1 to 2 of x dx, what you would do is find the antiderivative first, x squared over 2, right, plus c, and evaluate that at x equals 2, x equals 1, and so that would give you, well, 4 over 2, that's 2, and then you would subtract 1/2, right, and then that gives you 3/2. So for these ordinary definite integrals, we did something like that, where you had to find an antiderivative first, and essentially we want to do something similar for functions like that, functions which are of two variables. So it would turn out that expressions like this can also be integrated by sort of finding antiderivatives. The thing to realize is that there are two natural antiderivatives now, in the same way in which when you had a function like this, there were two natural partial derivatives to take. So as I will explain in a moment, the idea is that you can sort of do like a partial integral with respect to y, and then do like a partial integral with respect to x and get a number. Or conversely, you could have done first a partial integral with respect to x and then a partial integral with respect to y and get the same number. And that the fact that you will get the same number is called Fubini's theorem. So let's try to explain what the idea about that is. So the idea of Fubini is that you can compute by doing some partial integrals. So the standard name for partial integrals is not really partial integral, it's called like iterated integral. So known as iterated integrals. So what's the point of an iterated integral? This will become more clear with the animation I will show you in a moment, because on the computer it's just easier to see what's going on. But the idea is, again, going back to our original problem, we have the graph of this the graph of this function, which is surface. We want to compute the volume here, say between we want to compute the volume between the surface and this piece on the xy plane, this smaller rectangle on the xy plane. And so what we want to do, the idea of an iterated integral is that you compute this volume sort of by slicing the volumetric region into pieces, into smaller pieces. So say, for example, imagine that I fix, just to make this more concrete, let's say that this is 1, this is 2, and this is 1, and this is 3. Okay? So imagine that you choose a value between 1 and 2, let's say 1.5. So when you choose this value 1.5, this segment represents all the points on this square whose value of x is 1.5, right? So here you have fixed the value of x. So here x is fixed, right? And now imagine that out of this yellow segment you build a wall. So you lift it up. As you lift it up, then this will cross the surface into a curve, right? So you get here a curve, and now you get like a sheet of paper, a piece of paper, right, which is not necessarily rectangular because of this curvy part upstairs, but regardless of that, it has an area. Well, what's the equation of the curve? Notice that you have fixed the value of x to be 1.5. So in this particular case, the curve is z equals f of 1.5 comma y. Okay? So really, the area, let me draw it here downstairs. The area of this yellow piece, right? Well, this is now like a function of one variable, right? Because the only thing that's changing along this segment is the value of y. So you're integrating f of 1.5 y. So you're integrating over y from 1 to 3. Okay? So this is the area at x equals 1.5. And as you can imagine, the area at any x, right? What if you had chosen something that's not 1.5 but another number? Well, it would have been the same argument. So the area at fixed x equals a of x, which is the integral from 1 to 3 of f of x comma y dy. But the point that I want to emphasize here is that now x is fixed. So here x is like a constant. So in this notation, what we're doing is something similar to what we did with partial derivatives, where we would treat one of the variables as a constant. Here, the one that we're treating as a constant is x. And so later, what you would like to say is that, again, I'll show you in a moment the animation, is that as you move these yellow sheets of paper, right, as you sweep, you start sweeping out the entire volume of the region. So what you would like to say is that the volume is the sum. Remember that when you're trying to sum something that varies continuously, really you're doing like an integral. So really you're adding up all these areas, which you imagine have some tiny thickness dx. So imagine that this has some thickness dx, so this really gives you some amount of volume. Okay? And so you're really adding up all these pieces of area from 1 to 2, because those are the values that x can take. But if you plug in what a of x is supposed to be, you get the area, the integral from 1 to 2 of a of x. But a of x is just the integral from 1 to 3 of f of x y dy. Okay? So this is one approach for computing the volume. Here's the second approach. So let me draw this again because otherwise it will be too confusing. So again, the graph is that thing. Let's see if doing this explanation one more time makes things more clear. So you have the same rectangle as before. Here you have 1, 2. Here you have 1, 3. Okay? And now, rather than fixing a value of x, I'll fix a value of y first. So now I'll fix a value of, say, y equal to 2. So here's 2. Here you have this segment. Along this segment, y is equal to 2, right? So y is fixed. Now again, you imagine that from this segment you lift a wall. So you get some sort of curve upstairs, which has gives you a piece of paper with some area. So again, the formula for this curve, right, is z equals, well, now that the thing that you have set equal to a constant is y, right? So y was equal to 2, so you get z equals f of x comma 2. Okay? So what we want to say is that the area at y equals 2 is just what? Well, x is free to vary between 1 and 2. So it's the integral from 1 to 2 of f of x comma 2 dx. Okay? And so when you don't fix y equal to 2 but just to a different number and different value for y, a similar story happens. So the area at fixed y is a of y, which is the integral from 1 to 2 of f of x comma y dx. But now again, the point is that y is fixed now. So one more time, you're doing like some sort of partial integration because, as you'll see in the next video where I start doing some examples, the actual variable in this context is x, not y. And what you could do then is, again, you imagine you start varying this sheet of paper and you start sweeping, and the point is that you start sweeping out the entire volume of the region. Okay? So the volume in this case should also be what you get by adding the tiny pieces of area. So again, imagine that you introduce some thickness dy. So the little volumes that you're adding are a of y dy, which are being integrated. Now y can go from 1 to 3. But again, what is a of y is this integral that I wrote there. So the point of Fubini is that it should not matter in which order you decided to slice up the volumetric region. And so what Fubini is really saying, the content of Fubini, is that these two methods for computing the volume should be the same. So the volume computed using this approach will be the volume computed using the other approach. So what is it that has happened here comparing the two formulas? So essentially you see you have still the same function. The only thing that's being switched is the order of integration. So what this is going to mean in the next video is that first you're integrating here with respect to y. Okay, you will get something that depends on x because x was being held like a constant. So this is similar to a partial integral with respect to y. And then whatever you get, you will integrate with respect to x from 1 to 2. And what Fubini says is that what you could have done is reverse the roles. So first, you integrate with respect to x, considering y as a function, as a constant, and what you get will depend on y, and that gets integrated against y from 1 to 3, and will give you a final number. Okay, so I will show you right now the animation, so that hopefully it will make things more. So the essence of Fubini's theorem is that basically you can compute a double integral in terms of two iterated integrals, which is the analog of taking partial derivatives when we were studying functions of two variables. So to make this more precise, we have this function here of x and y. Again, the graph of the function looks like a surface, which is this red surface that you see here. And so we're trying to compute the volume between this surface and the floor. And what Fubini's theorem says is that basically you can compute this volume by adding up a bunch of cross sections of area. So basically, as you see here, we have this yellow cross section, and the idea is as you vary this yellow cross section, right? Imagine that it has a very tiny thickness so that it actually contains some volume. As you vary the cross section, then you recover all the volume. And in this particular case, we are using the order of integration dy dx, which again means the following. You fix a value of x, right? So here the value of x that I'm fixing is equal to 1. So once you fix that value of x equal to 1, above that line, you get like a wall that intersects the surface into a curve, right? So here's the curve of intersection. And so the area becomes like the ordinary the area becomes the ordinary integral that you know for functions of one variable. And then what we do is vary this wall and add up all these areas, which is what you see here. So the content of the first part of Fubini's theorem is saying that this volume can be computed by adding up all these tiny pieces of area, or really more precisely tiny pieces of volume, right? Because ax dx has units of volume. And the second part says that you could have sliced up this region in a different way, which is what happens when you reverse the order of integration. So now I switch to the order dx dy, and again that means the following. Here I'm fixing now a value of y0 first, so y is equal to 2. This gives you a wall which intersects the graph in some curve, which is the one that you see here. And then there's again like a very tiny volume associated to this wall if you imagine that you thicken it a little bit. And what Fubini's theorem says is that as you vary this wall and start adding up all the tiny volumes together, which is doing this integral, then you get back the volume of the entire region. And that really it does not matter in which way you decide to slice up your region of integration. Clear. Okay, now that you saw the animation, let me just mention briefly what triple integrals are. Again, I'll do an example about it in the next video. But so for a single integral, we have something like y equals f of x, and we would consider an expression like the integral of a to b of f of x dx. For a double integral, as will become more clear later, again we have something like c equals f of x y, and analogously we will consider something like c to d a to b of f of x y, let's say dx dy. And then, as you can imagine, then for a triple integral, right, so y, c, so we run out of letters, so we go back to w. So you would write something like w equals f of x, y, z, right? The problem, I mean, not the problem, it's just that we cannot really visualize it very easily. What you would like to think is sort of that here are x, y, and z as three perpendicular axes, and then you have this new axis w as a fourth dimension, right? The problem is that I cannot really represent that on the blackboard, not even in free space. If I were trying to draw it with like do it physically, but you imagine you have three axes for the independent variables, a fourth axis for the dependent variable, and then here you had a curve, here you had a surface, so the graph now looks like a 3D thing here. So it's now like a thickened surface. So the graph is some sort of 3D body. And then there's some sort of hypervolume between this thickened body and the floor, but the floor is now XYZ space. So now here's some hypervolume. And what you would like to say is that that's what is being represented when you do an integral. Let's say you're integrating this hypervolume over some 3D region R. So again, you imagine that you're approximating this by boxes of height f and small volume dv, okay? And you add them all together, and that's how you get the value of this triple integral. In practice, since we cannot really visualize this, this is not the most useful interpretation of a triple integral. We'll see some later. For example, just when you happen to think of this function as a density function, so if this happens to be like a mass density, so density times volume has units of mass, and this just happens to compute like the total mass of an object, which is a lot more concrete than saying something like hypervolume. So really you have to think about the specific context to see whether or not your integral has some more interesting interpretation. But the point about this is that regardless of the fact that we cannot really represent this very clearly, there's still like a Fubini version where you would still be able to slice this up into regions. It's just that before the slices were like sheets of paper, now the slices are like actual volumetric things, and then you vary them. And again, you'll see that with the examples it's a lot easier than how it sounds like. But basically the 3D version of Fubini just tells you the same as before, namely that you can move things around in a way that's convenient for you. So again, I'll teach you next time how to interpret this expression, but the idea is that you sort of read it from the inside to the outside. So you're integrating first with respect to c. When you integrate first with respect to c, x and y are being considered constants. After you do this integration, then you integrate with respect to y, and x will be considered constant. And finally, you integrate with respect to x, and then you get a number. But what Fubini will say is that you can sort of reverse the order of integration in the same way in which you can compute partial derivatives in different orders. So again, you keep the same function that never changes, but maybe you want to reverse the roles of x and y, so you want to flip those two around. So let me just put here the x, the c, and put the y still in the middle. And the point is that you can do that. You didn't move the one in the middle, so the bounds for the one in the middle remain the same, but you flip the exterior with the interior, so you flip the corresponding bounds. So you put 3, 5 here and 1, 2 here. And now you're doing an integral first with respect to x, and then an integral with respect to y, and finally what you get, you integrate with respect to c. And as you will see in a moment, in the next video, you'll see that we get actually the same answer.